We want to put the H and make this have a plus charge. Again, we're doing this, right? Why do we protonate? Right? Why are we using these acid conditions versus the basic and neutral? This, when you protonate, this carbon, again, this carbon right here, becomes more delta plus, so more susceptible to a nucleophile attack. So it's a better electrophile. That's why we protonate it. All right, so the mechanism here, protonation makes things a better leaving group. Right? As when we have a plus charge on something, it's a better leaving group than something without a plus charge. Right? So acid catalyzed can make it a better leaving group than with not having the acid. Just a little bit of a side note here. This is interesting. I want to show everybody. If we have a tert-butyl off here, we actually go through a different mechanism. We actually have an SN1, an internal SN1 take place. Now, why would we do that? As we protonate, right, a tertiary carbocation is very stable, so as these electrons break, those electrons go up. We get the carboxylic acid in one step. We make a tertiary carbocation, which then can get attacked. We get the tertiary alcohol. So it's a little different with the tertiary alkyl group, the different little mechanism there. It goes through an SN1. So now we're going to have, essentially I'm going to show you two ways to take an ester. Right? I've shown you ester in acidic conditions. Right, now it's catalyzed. Now I'm going to show you ester in a basic condition. Right? And this is all hydrolysis. Right? Turning an ester into a carboxylic acid. So this step here, if we had OH minus, right? So now we're in basic conditions. Right? Negative charges. Attacks the electrophilic carbon of the carbonyl. Electrons go up. Tetrahedral intermediate. Now there's a choice here. I would say we can kick out the OCH3, and if we do that, we get to a carboxylic acid, which then can get immediately deprotonated, right? Deprotonated by what just came off, and we make methanol and this carboxylate. Now this is a really bad electrophile, right? This carbon here, you can see there's a minus charge here now. There's a lot of resonance. It's going to make that carbon not reactive, right? So that's just going to sit there, right? So once we make that, it's over. Right? Yes, at this point, right, OCH3 could come off, or OH could come off, but then it could always come back on. Essentially what happens is you attack here, kick out the OCH3, you make the carboxylic acid, and then the carboxylic acid actually acts like an acid, right, where this H gets removed by this strong base that you just kicked off. The big difference here is between this acidic condition, ester, to turn an ester into an acid, versus the basic condition to turn an ester into an acid. The acidic one's reversible. Note the arrows. Right? That's an equilibrium arrow. It can go back and forth, right? If I add a bunch of methanol, right, if I add a bunch of methanol here, I could shift it back this way. If I add a bunch of water, I could shift it this way. With this basic, it's a little different. Because you make this carboxylate, which is so unreactive, right, versus this plain carboxylic acid, right? Getting rid of this H makes all the difference in the world. That much more. That makes this carbon that much more not delta plus, not reactive. With NaOH, it's irreversible. It's also not catalyzed. All right, acid is catalyzed. Right, you regenerate the HCl. This is not catalyzed. All right, it's a big difference. All right. Now, what if I want to do an ester to an ester? All right, so what about this transesterification? So ester to ester. Right, the first one we're going to learn about is in basic conditions. So what do you think happens here? We know this works here. So I'm going to show the basic conditions, and then I'll also show the acidic conditions as well. So let's see, let's do the basic one first. And we're going to do it in ethanol. And what's going to happen is basic conditions are nucleophile, attacks the carbon of the carbonyl, that's delta plus. We get a tetrahedral intermediate, right? So this is that addition step, add in O. Now we have a choice to make, and I'm going to kick out this one, right? Just because there's probably more of this floating around. Now that's a better leaving group, that we're just going to drive equilibrium that way. We're going to put a lot of this in there to help drive equilibrium. So that's this elimination step, of course. We went from sp3 back to sp2 now. And now we have the new ester plus that, right? And this is, of course, in basic conditions with a negative charge. This is that transesterification. Transesterification. Good. Now, what if we want to do this in acid? What would that look like? So let's shrink this guy down a little bit, put him over there. Now let's take a look. If I was going to take this exact same set of things, and now I'm going to do it in ethanol, but I'm going to use H+. Now the first step, the oxygen, the more electron-rich oxygen attacks. That's, of course, making the carbonyl carbon more delta plus. Right? That helps activate this carbon right there. Now, in this case, the solvent is going to play a role. The ethanol solvent is now going to be the nucleophile because we've made this carbon of the carbonyl more electrophilic. So now that can attack. Make this tetrahedral intermediate. Of course, this is that addition step. Tetrahedral intermediate. Balance our charge. There's a plus charge there. Now we're going to do that proton transfer we've talked about. Right? And you can draw the arrows. It's probably from an intermolecular process. The angles don't quite work out, but if you want to draw arrows, that helps. Make you see it better. Turn that other part into a better leaving group now. Right? Again, these are all equilibrium reactions. We can drive equilibrium by having, right, a lot of reagents around the star material, so form products. Now this next step, now we have a better leaving group. These electrons come down. The better leaving group leaves, the protonated one. We want to make sure we're always balancing our charges as we go. So now we've made the ethyl ester. We've also made methanol. And then the last step, we're going to regenerate our catalyst, right? And these transesterifications are also acid catalyzed, so we remake the H+. So that's the difference here between this acidic transesterification, which is catalyzed, versus the basic transesterification, which of course is not. Plus charges, minus charges. So finally, to wrap this kind of up, this is a nice, interesting discussion about how do we know this isn't an SN2 reaction? How do we know it's not a one-step? How do we know it's not SN2? How do we know it's an actual addition elimination step where we go through an sp2 to an sp3 back to an sp2? How do we know we add in and then eliminate? The way they've done this is that essentially they've labeled one of the oxygens in an ester. And this is all this means is essentially isotope labeling, right? So imagine that 18, so it has an oxygen with a couple extra neutrons, that's starred. If you did an SN2, essentially what that would mean, if you did an SN2, that this O18 would always be in the products within a hydroxyl, right? If you did an SN2, you would always have the O18, what I'm starring here, would always be in the products. But what they found out was that it wasn't, right? If we're doing an SN2, the O18 would have to be in the products, right? But it's not, and that's the key. And you can look through this little mechanism here. It's a nice little study here showing how the O18 sometimes can be the part that gets kicked out. And the O18 will actually not end up being in the final product ester, which indicates to us that an SN2 is not possible, right? So that's the kind of the nice little side story there. That's proof that, somewhat proof that tetrahedral intermediates form, because if it was an SN2, the O18 would always be in the final products with this starting material.